Now what I'm going to do, see, I'm going to take ideal gases. Okay, so let me take two containers like this, or I'll take a container like this, and I'll put a partition here, partition. So this container is separated into two compartments. In compartment 1, I'll take some gas A, and in compartment 2, I'll take another gas B. Okay, I have two gases now, right? And say number of moles of gas A, let it be Na, and number of moles of gas B, let it be Nb, right? And let us assume the pressure of this gas as P, and this gas also P, and temperature, let it be T. Here also temperature is T. So both the gases, okay, are in same pressure and same temperature. Both the gases are in same pressure and same temperature. Okay. Now what I'm going to do, I'm going to find out delta S mixing first. Entropy change of mixing. We'll find out this first. Okay. Now what I'm going to do, listen. Suppose if I remove the partition, okay, the gas mixes. Okay, initially I have only gas A here and only gas B here. So I have pure gases. Now if I remove this partition, the two gases starts to mix. So I'll get mixture of A and B here. You have A and B. And suppose, assume that the final pressure and temperature also same. Okay, that means pressure remains constant during this mixing. Right? We are mixing gases. Here A and B are ideal gases. Remember? A and B are ideal gases. That is very important. We are mixing ideal gases. Okay. Now, first we'll find out what is the delta S mixing. Delta S for A, gas A alone. Change in entropy of gas A. Change in entropy of gas A. Observe this carefully. You know very well, for ideal gases, delta S formula, you know very well this formula, N into, okay, see, pressure is constant, right? See, for gas A, initial pressure is P. After mixing also, the final pressure also same, P. So pressure remains constant. At constant pressure, you can write delta S as equal to N into CPM, okay, into dt, or ln, let me write here, ln T2 by T1, okay, plus, observe carefully, minus NR ln P2 by P1. Note down. This is an equation used to calculate change in entropy for a gas. Now we are going to find out change in entropy for gas A first. Okay, observe carefully. Here temperature is constant. Therefore this becomes 0. This is going to be 0. Right? Now delta S for gas A equal to minus N here is number of moles of gas A into gas constant R ln, what is the initial pressure? That is nothing but pressure of the gas A, which is nothing but P. Observe carefully. Initial pressure is nothing but pressure of the gas A, which is nothing but P. Now we need to find out the final pressure of A in the mixture. Observe carefully. This is total pressure. This P is total pressure, but we need to find out what is the pressure of A in the mixture. It is called partial pressure. Let me write this as PA. What is PA? PA is nothing but partial pressure. Partial pressure of A in the mixture. And you know very well, for ideal gas, what is partial pressure? Partial pressure is equal to mole fraction of into total pressure. Correct? This is applicable for ideal gas. For ideal gas, Okay, partial pressure equal to mole fraction in total pressure. Substitute this here. So what we get is minus number of moles of A into gas constant R ln, instead of PA I'll put mole fraction A into total pressure by P. This P and this P are same, so I can cancel these two. So what we get is minus number of moles of A into R into ln XA. This is change in entropy of A alone. Change in Similarly, for gas B, we should write the same equation, delta S, change in entropy of gas B equal to number of moles of gas B R ln mole fraction of gas B. Okay, we can write like this for gas B. So we need to find out delta S mixing. I'll write here. So what is delta S mixing? Delta S mixing equal to change in entropy of gas A plus change in entropy of gas B. Okay, what is change in entropy of gas A? Let me write minus number of moles of A into R ln XA. Right? Here we should put minus, but here we have plus, so plus into minus is minus, so I'll put minus number of moles of B R ln XB. Okay, listen, here we have R, here we have R, so R is constant, you can take it out. You can also take minus as common, so minus R, okay, and I can write summation. You need not write for gas. Listen, minus R summation, you need not write for gas A, gas B separately, okay. You can write in general like this. How? Number of moles of ith gas into ln xi. You can write like this. Listen, here I took only 2 gases and I mixed. You can take 3 gases, you can mix. You can take even 100 ideal gases and you can mix. Okay, and this is the general formula, okay, for mixing. Right? So this is delta S mixing, but here this is delta S mixing for total moles. Total mole, what is total mole? Na plus Nb. For this much number of moles, total moles, see, number of moles of A may be 5 moles, number of moles of B may be say 2 moles. So total is 7 mole. For 7 moles, this is the change in entropy of mixing. But sometimes they'll ask you to find out what is the change in mixing for 1 mole of mixture. Okay, so for 1 mole of mixture, here 7 mole of mixture is there. For 1 mole, what to do? This is n mole. N is the number of moles of the mixture. For n mole, this is the formula. Now I am asking for 1 mole. What to do? For 1 mole of the mixture, can anyone tell me what we have to do?
Divided by Na plus Nb.
Divided by n, that's all. Yes, Na plus Nb or n. Okay, so delta S mixing, okay, per mole of the mixture, per mole of the mixture, okay, keep this in mind, equal to minus R, right, divided by n we have to put, but I can bring n inside. You can bring n inside, so I'll get Ni by n ln xi. What is Ni by n? Ni is the number of moles of ith gas. This n is total number of moles. So this is nothing but mole fraction again. So you'll get minus R into summation xi ln xi. Yes, this is the formula for delta S mixing for 1 mole of the mixture. Okay, take note.
Yes, sir.
Yeah, see, now we are going to find out delta G mixing, and you know very well Gibbs free energy for any substance or any mixture, Gibbs free energy of the mixture is equal to summation Ni into mu I. Ni is nothing but number of moles of ith component. Mu I is the chemical potential of the ith component. Okay, suppose if I mix ideal gases, see, for ideal gas, okay, what is the chemical potential of the ith gas? For ideal gas, mu I equal to mu I naught plus RT ln P, pressure of the gas. For ideal gas, mu I equal to mu I naught plus RT ln P is well known. So what I'm going to do, listen, what is the Gibbs free energy before mixing? Okay, or initial. Gibbs free energy in the initial stage. Gibbs free energy in the initial state is nothing but Gibbs free energy of gas A plus Gibbs free energy of gas B. Okay, what is the Gibbs free energy according to this? Okay, for gas A, what is the number of moles? Na moles of gas
Sigma
A.
Na mu A.
Yeah, then chemical potential of gas A plus Gb is nothing but number of moles of gas B into chemical potential of gas B. Okay, now number of moles of A, you keep it as such. What is chemical potential of A for ideal gas? See, A and B are ideal gases. So for ideal gas, we can write chemical potential of mu A naught. Okay, chemical potential in the standard state plus RT ln, right, PA, pressure of A, PA before mixing, okay, plus number of moles of B into this, okay, chemical potential, standard chemical potential of B plus RT ln pressure of B, right. So this is the Gibbs free energy before mixing or initial, right. I can also write before mixing. Now what is the Gibbs free energy after mixing? After mixing, let me write GF final, Gibbs free energy final. See, after mixing we have a mixture now, right. For the mixture, how to find this chemical potential and all, okay, we'll do. See, number of moles of A, right, into chemical potential of A in the mixture, right, chemical potential of A in the mixture plus number of moles of B into chemical potential of B in the mixture, right. This is in the mixture. I'll put mix, okay. Now listen, keep this number of moles of A as such. What is the chemical potential of A in the mixture? It's nothing but standard chemical potential of A plus RT ln. Now in the place of pressure, you should put partial pressure of A. This is actually partial pressure because we are calculating chemical potential in the mixture, right, plus number of moles of B into standard chemical potential of B plus RT ln partial pressure of B. Okay, take down. So this is nothing but partial pressure of B in the mixture. Since A and B are ideal gases, you know very well the partial pressure is equal to mole fraction into total pressure. Okay, so let me write that in the next page. Let me write here. Observe carefully. So I'll keep this Na as such. Okay, if you want, you can also multiply here Na into mu naught A plus Na into RT ln partial pressure of A. Since A and B are ideal gases, partial pressure of A is nothing but mole fraction of A into total pressure, okay, P. Then plus here I'll write number of moles of B into mu naught B plus number of moles of B into RT ln partial pressure of B is nothing but mole fraction of B into total pressure, right. Now what I'm going to do, observe carefully. It's very simple actually, okay. Na mu naught A plus here I have XA and into P. In logarithm, if you have A into B, we can take it as log A plus log B. So I can separate this into Na into RT ln XA plus Na into RT ln P. Okay, then here similarly plus I'll keep this NB into mu naught B as such, and here also we can write in a similar manner NB into RT ln XB plus NB into RT ln P. Now listen, I am going to take this term this term, and this term, right? So I have number of moles of A here, number of moles of A here, number of moles of B, number of moles of B here. So let me write this as number of moles of A into mu naught A plus this term RT ln P, right? Then plus number of moles of B into mu naught B plus RT ln P. Then the remaining term, what are the remaining terms we have? Number of moles of A into RT ln XA plus number of moles of B into RT ln XB. Right? Now, observe carefully. What is GI? Gibbs free energy in the initial stage. Listen, you know very well, before mixing, this PA, pressure of A, this is not partial pressure, this is pressure of pure gas A, this is pressure of pure gas B. I have told you these are all equal, and this total pressure, they are all equal, correct? This is what I said. See in the diagram, this is pressure of A, this is pressure of B. So A pressure, B pressure, and the total pressure all are same. Are you able to understand? So this quantity, see here, this quantity is nothing but GI. So here I have GF. So GF is equal to, this quantity is nothing but GI plus, see, for gas A I have this term, for gas B I have this term. Suppose if I take gas C, gas D, I'll get similar terms like this. So I can write directly that as Na is RT is constant, summation Ni ln Xi, we can write like this. Bring this GI to the left hand side. Gibbs free energy in the final state minus Gibbs free energy in the initial state is nothing but delta G mixing. So delta G mixing equal to RT summation Ni ln Xi. So this will give you delta G mixing for n moles of the mixture. For n mole of the mixture, this is the delta G mixing. For 1 mole, what to do?
By N.
Divided by N. That's all. So for 1 mole, delta G mixing per mole of the mixture equal to, you have to divide by N. So N is nothing but total number of moles. So RT into summation Ni by N. If I divide this by N,
Psi.
Okay, Xi into ln X. Yes, you are right. Yes. So this is for 1 mole of the mixture. Okay, take note. So for this gas mixing, ideal gas mixing, we found out that delta S mixing for n mole of mixture. Okay, I am writing for n mole. For n mole of mixture. For n mole of mixture, delta S mixing equal to minus R into summation Ni ln Xi. Right? And delta G mixing for n mole equal to minus plus RT summation Ni ln Xi. Right? Now observe this carefully. You know very well delta G is equal to delta H minus T delta S at constant temperature, right? At constant temperature, delta G is equal to delta H minus T delta S. Right? Then what is delta H? Bring this term to the left hand side. So delta H is equal to delta G plus T delta S, correct? Now delta H mixing equal to delta G of mixing plus T into delta S of mixing. What is delta G mixing? RT summation of Ni ln
Xi.
Xi, correct? This is delta G mixing. Right? What is delta S mixing? Delta S mixing is minus. Now we have to multiply by T. So what we'll get? Minus RT. Am I right?
Summation of Ni ln Xi.
See, these two quantities are equal, correct? If I subtract,
0, sir.
Yes. For ideal gas mixture, delta H mixing is 0. If you mix 2 or more ideal gases, okay, there is no change in the enthalpy. No heat is released, no heat is absorbed. Okay, delta H mixing is 0 for mixing of ideal gas. For mixing of ideal gases. Okay, take note. See how to find delta V mixing. See, you know very well, according to standard equation, okay, delta H or DH or delta H is equal to, observe this formula carefully, T into delta S plus P into delta, I'm sorry,
VDP, sir.
VDP.
V.
One second.
U plus PV.
One second. I'm sorry. See, first I'll do for internal energy, then I'll come here. Change in internal energy of mixing. Enthalpy of mixing we discussed. Now we'll discuss change in internal energy of mixing. Once we found this, then we'll go to delta V mixing. Okay. See, you know very well, H is equal to U plus PV. Right? H is equal to U plus PV. So delta H is equal to delta U at constant pressure, it is P into delta V. P delta V at constant pressure. Okay. I'm sorry, I made a mistake. One second. Therefore, for mixing of ideal gases, right? For mixing of ideal gases, number 1, we discussed what is delta S mixing, which is equal to minus R summation Ni ln Xi. This formula is applicable for n mole of gas or n mole of the mixture. Okay. Then delta G mixing we have found out, which is minus RT summation Ni ln Xi. This is delta G mixing for n mole of the mixture. Then we found out that delta H mixing equal to 0. Right? Then fourth one, we also found out that delta V mixing is also 0. Okay. Then fifth one, delta U mixing. Right? You know very well. Once you know delta V, you can calculate delta U also. Delta H is equal to delta U plus P into delta V. So delta H mixing equal to delta U mixing plus P into delta V of mixing. Right? This is 0, you know. Delta U mixing we need to find out. Delta V mixing also 0, so this becomes 0. Therefore, delta U mixing, internal energy change of mixing is also 0 for the mixing of ideal gases. Okay, take 2. Remember all these results. Okay. Now, 1 mole of CO2 gas, 1 mole of nitrogen gas, 2 moles of oxygen gas, okay, are mixed at 300 Kelvin. So, we will get a mixture. Now, we need to calculate what is delta S mixing. Assume that all these gases are ideal gases. Okay. It is not given in the question, but anyway, you assume these gases as ideal gases. Ideal gases. Okay. Now, listen. Since they are ideal gases, we can use the general formula delta S mixing. Delta S mixing equal to, this is the general formula, minus R into summation Ni ln Xi. Okay. Ni ln Xi. This is for n moles of the mixture. But what is the n here? N is equal to 1 plus 1 plus 2, which is 4 moles.
4 moles.
Yeah, so we have 4 moles of the mixture. For 4 moles, what is the delta S mixing? We are going to calculate. Okay, so keep this minus R as such. Right? Then First, I'll take the first gas. Number of mole is 1 mole. Ln, what is the mole fraction of first gas? CO2 gas, we have 1 mole. And total
1 by
number of
4.
moles, yes, 1 by 4. Very good, sir. 1 by 4. Plus, summation is there, so plus.
1 by 4.
Next, 1 into ln
1 by 4.
1 by 4 again, very good. Plus 2 into ln 2 by 4. Let's say 2 by 4 is something but
1 by 2.
1 by 2. Okay. So what we get is minus r into
சார் இங்க psi தானே சார் நம்ம எடுப்போம்.
ln 1 by 4 is nothing but minus ln 4. Okay, here I have plus 1 into this is same. Ln 1 by 4 is minus ln 4, and here plus 2 into ln 1 by 2 is minus ln 2. Minus ln 2. Okay. Now what I am going to do, according to power rule, you can bring this 2 to the power here. So what we get is minus r into minus ln 4 minus ln 4 minus, if we bring this 2 here, 2 power 2 is 4, so this is also ln 4. I have minus 1 ln 4 minus 1 ln 4 minus 1 ln 4. If I add, I'll get minus r into minus 3 ln 4. Okay. If this is minus x, I'll get minus 3x. So minus 3 ln 4. Minus or minus become minus or minus plus. So plus 3r ln 4. This is the answer for this question. So in the option it is given as 6r ln 2. 6r ln, this option is not there, but 6r ln 2 is there, which means you can write 4 as 2 power 2. Bring this 2 in front. So 3 into 2 is 6. So I can write it as 6r ln 2. 6r ln 2. So this answer for this question. Okay, take note. Yeah. So third law of thermodynamics. Third law of thermodynamics. What is this actually? Listen, this third law will give you an idea about calculation of molar entropy or entropy at a particular state. Actually, for internal energy, we can find only change in internal energy. We cannot find internal energy at a given state. This is not possible. We can find only change in internal energy. Similarly, enthalpy at a given state is not possible. We cannot calculate. We cannot determine experimentally. Only what we can do is only change in enthalpy. Right? But for entropy, yes, individual entropy at a particular state, we can calculate or we can measure experimentally by using this law called third law of thermodynamics. Okay, third law of thermodynamics. Right? So what is third law? Listen. The third law, according to this law, the entropy of a perfectly crystalline substance. See, this is a definition. Entropy of a perfectly crystalline substance or solid. Entropy of a perfectly crystalline solid is 0 at 0 Kelvin. Take note. This is what we call as third law of thermodynamics. So you know very well for a closed system, okay, change in internal energy or change in enthalpy for a closed system, we can write it as TdS plus VdP, right? TdS plus VdP at constant pressure. If we keep pressure constant, dP becomes 0. Therefore, I can write dH is equal to TdS. Right? Then what is ds? ds is equal to dH by T. Okay. And you know very well, dH is nothing but Cp, right?
Delta QP.
Yes. Cp into dt. Or I can write N into Cpm into dt by T. right? If I integrate both sides, I'll get delta S in the left hand side, delta S equal to, right here I'll get n into CPM integral n into CPM, right, into dt by t. I'll get this term. Observe this carefully. What is delta S? Entropy. See, we have to integrate from T1 to T2. We have to integrate from T1 to T2. What is delta S? Entropy in the final temperature T2 minus entropy in the final temperature, in the initial temperature T1. That is delta S, which is equal to integral T1 to T2 n into CPM into dt by t. This we know. Okay, suppose if we take initial temperature as 0 Kelvin, observe carefully. I'll take initial temperature as 0 Kelvin, right? And see, at 0 Kelvin, you will have only solid. If it is a perfectly crystalline solid, then what is the entropy? I am taking T1 as 0 Kelvin. Okay, so what is the entropy at 0 Kelvin for perfect crystalline solid?
0.
0. So this I am going to make this as 0.
0.
If I make this as 0, then entropy at any temperature T2, let me write simply T, is equal to integral T1 is 0 now, 0 to T, okay, n into CPM into dt by t. Right? What do you infer from this equation? Tell me. What do you infer from there? Delta S is equal to n CPM dt by t. Okay, this is the formula. Initial temperature T1, final temperature T2. And what is delta S? Delta S is nothing but entropy. Since entropy is a state function, delta S is nothing but entropy in the final state T2 minus entropy at the final initial temperature T1. Okay. Suppose if I keep T1 as 0 Kelvin and at 0 Kelvin substances exist as solid, correct? At 0 Kelvin, if the solid is perfectly crystalline solid, then entropy should be 0. Therefore, this entropy becomes 0 at 0 Kelvin. If this is 0, then we will have only this entropy. Okay, in the place of T2, you just put T here outer. So, entropy at temperature T is equal to integral. So, now T1 becomes 0 and in the place of T2, you put just T. 0 to T n CPM dt by t. Right? Now, this is for n mole of substance. For 1 mole, divide both sides by number of moles. Okay. So, if I divide by number of mole, I will get molar entropy at temperature T equal to this n cancel. Okay. Here I have n. Here I have n. That n cancels. So, I will get CPM into dt by t. And while deriving this, I said pressure should be constant. If I keep that constant pressure as P0, what is P0? Standard pressure. Then that entropy is can be called as standard molar entropy of the substance. Standard molar entropy at temperature T. Okay. Yes. And this right hand side quantity is experimentally determinable quantity. We can determine through experiment. Okay. Take down.